3.2. The derivative as a function. The outline of this video is as follows. We will begin by introducing an alternative formula for the derivative, giving us another powerful tool for calculating derivatives directly from the definition. From there, I will show you several different notations used to represent the derivative, as these will be essential for our future work. Next, we will explore the visual relationship between a function and its derivative by learning how to graph the derivative. We will then refine our understanding of where a derivative exists by examining one-sided derivatives, which helps us analyze functions at points like sharp corners or endpoints. Finally, we will clarify the crucial connection between differentiability and continuity, exploring how one property implies the other and what that means for the functions we analyze. I am now going to generalize the concept of the derivative from a single point to an entire function, which is a powerful step. We define the derivative of a function f of x as a new function, which we call f prime of x, that gives the slope of the original function at any value of x. This is calculated using the same limit we saw before. The limit as h approaches 0 of the quantity f of x plus h minus f of x, all divided by h. When this limit exists for a particular x, we say the function is differentiable at that point. For example, for a smooth curve, this new function tells us the steepness at every location along that curve. It is important to know that the domain of this derivative function can be smaller than the original function's domain, because the limit might not exist at certain points, like at a sharp corner. The key takeaway is that differentiation is an operation that takes one function and gives us another that describes its rate of change everywhere. We can express the derivative using a slightly different but equivalent formula that is often more convenient to work with. The key idea is a simple change of variables from our original h approaches 0 definition. Instead of thinking about a point x and a second point x plus h, let us give that second point a new name, z. If z equals x plus h, then the distance h is simply z minus x. Now for the distance h to approach 0, the point z must get closer and closer to the point x. Substituting these expressions gives us our alternative formula. F prime of x equals the limit as z approaches x of the quantity f of z minus f of x, all divided by the quantity z minus x. This nicely represents the derivative as the limiting slope of the secant line between a fixed point at x and a moving point at z. Let us apply the limit definition to find the derivative of the rational function f of x equals x over the quantity x minus 1. This example is a great way to see how the definition works, even when the algebra gets more involved. We begin by substituting the expressions for f of the quantity x plus h and f of x into the difference quotient, which creates a complex fraction. The key step to simplifying this is to find a common denominator for the terms in the numerator. After we expand the products, we see a helpful pattern where many terms cancel out, leaving just negative oomph in the new numerator. This allows us to cancel the oomph from the top and bottom of the main fraction, which is the crucial step that let us solve the limit. Finally, letting the remaining h go to 0 gives our result. The derivative, f prime of x, is negative 1 over the quantity x minus 1 squared. This shows that the fundamental definition of the derivative is a reliable tool for any differentiable function. Let us find the derivative of the square root function, which requires a clever algebraic technique when using the alternative limit formula. We begin by setting up the difference quotient, which is the limit of the quantity square root of z minus square root of x, all divided by the quantity z minus x. The key step here is to recognize that the denominator, z minus x, can be factored as a difference of squares involving roots. Specifically, it is equal to the quantity square root of z minus square root of x times the quantity square root of z plus square root of x. This allows us to cancel the term square root of z minus square root of x from the numerator and denominator. We are left with the much simpler limit of 1 over the quantity square root of z plus square root of x. As z approaches x, this expression becomes 1 over 2 times the square root of x. Therefore, the derivative of the square root of x is 1 divided by 2 times the square root of x. Now that we have the derivative, we can use it to find the equation of the tangent line at a specific point on the curve. Our goal is to find the line tangent to y equals the square root of x, precisely where x equals 4. First, we need the slope at that point, which we get by evaluating our derivative function. Plugging x equals 4 into f prime of x gives us 1 over the quantity 2 times the square root of 4, which simplifies to a slope of 1/4. Next, we need the point of tangency itself, which comes from the original function, giving us the point 4, 2. With a slope of 1/4 and the point 4, 2, we use the point slope formula. Y minus 2 equals 1/4 times the quantity x minus 4. Simplifying this gives us the final equation, y equals 1/4 x plus 1. The derivative function gives us the exact slope we need for the tangent line at any point. Now that we understand what a derivative is, let us learn the different ways to write it down, because you will see all of these notations used. The most compact forms are the prime notations, such as f prime of x or y prime. Another very common way is Leibniz notation, which looks like a fraction dy over dx, and is read as the derivative of y with respect to x. The symbols d over dx and capital D are called differentiation operators, which are simply instructions to perform the action of differentiation on a function. To indicate the value at a specific point, we can write f prime of a, or use a vertical bar to show where we are evaluating the derivative. For example, the derivative of the square root of x, evaluated at x equals 4, is 1/4. The main thing to remember is that all these symbols mean the same thing: the instantaneous rate of change. We can visualize the derivative as its own function by graphing it, which gives us a powerful way to understand the behavior of our original function. The derivative function, which we call f prime of x, is simply a new function whose value at any x is the slope of the original function f of x at that same point. To sketch this graph, I can look at the original function and estimate the slope of its tangent line at several key points, then plot these slope values on a new set of axes. For instance, wherever the original function has a flat, horizontal tangent, its slope is 0, so the graph of the derivative will cross the x-axis at that exact spot. This new graph reveals where the original function's rate of change is positive, negative, or 0, and even shows if that rate is itself speeding up or slowing down. This graph gives us a complete picture of where the original function is increasing or decreasing. Now that we can find a derivative at a single point, let us extend this idea to an entire interval, which requires a special look at the endpoints. A function is differentiable on an open interval if it simply has a derivative at every point inside. For a closed interval, which includes its endpoints a and b, we also need the one-sided derivatives at the boundaries to exist. At the start point a, we can only approach from the right, giving us the right-hand derivative, which is the limit as h approaches 0 from the positive side of the fraction f of the quantity a plus h minus f of a all over h. Similarly, at the endpoint b, we can only approach from the left, giving us the left-hand derivative where h approaches 0 from the negative side. So, for a function to be differentiable on a closed interval, it must be smooth everywhere inside and have well-defined, finite slopes at its very ends. Let us use one-sided derivatives to see why the absolute value function is not differentiable at x equals 0, which is a key example. Away from the origin, the function is quite straightforward. For any positive value of x, the derivative of the absolute value of x is simply the derivative of x, which is 1. For any negative value of x, the derivative of the absolute value of x is the derivative of negative x, which is negative 1. The interesting part is at the origin itself. To find the derivative there, we must check if the one-sided limits of the difference quotient agree. The right-hand derivative, approaching 0 from the positive side, evaluates to 1. But the left-hand derivative, approaching from the negative side, evaluates to -1. This mismatch is what creates the sharp corner you see in the graph. Because these two one-sided derivatives are not equal, the function is not differentiable at x equals 0. For a function to have a derivative at a point, its graph must be smooth and locally linear. I will now explain 4 common ways a function can fail this condition. First is a corner, which is a sharp point where the slope changes abruptly. For example, the absolute value of x at the origin has a slope of -1 from the left and +1 from the right, so there is no single limiting slope. Second is a cusp, an even sharper point where second slopes approach infinity from one side and -infinity from the other. Third is a vertical tangent, where the tangent line becomes vertical and its slope is undefined, like the graph of y equals x to the power of 1/3 at the origin. Finally, a function cannot be differentiable at a discontinuity, because if the graph has a break or a jump, there is no well-defined tangent line. In short, differentiability is a stronger condition than continuity, requiring a smooth curve with no sharp points, vertical tangents, or gaps. Let us explore the fundamental relationship between differentiability and continuity. This theorem establishes a key rule. If a function has a derivative at a point C, then it must also be continuous at that point. The proof relies on a simple algebraic rearrangement. We can write f of x as f of c plus the fraction f of x minus f of c over x minus c, all multiplied by the quantity x minus circa. Now when we take the limit as x approaches c, that fraction becomes the definition of the derivative, f prime of circa. At the same time, the quantity x minus c goes to 0. Since the derivative f prime of c is a finite number, its product with 0 is just 0. This leaves us with the result that the limit of f of x is simply f of c, which is the definition of continuity. Intuitively, this means a function cannot have a well-defined tangent line at a point where there is a gap or a jump. Differentiability is therefore a stronger condition than continuity. Now I want to address a very important distinction regarding the relationship between continuity and differentiability. While we know that a function must be continuous to be differentiable, the reverse is not true, which is a common point of confusion. A function can be perfectly continuous at a point, but still fail to have a derivative there. The classic example we have already seen is the function y equals the absolute value of x. This function's graph is a V-shape that is continuous everywhere. You can draw the entire graph without lifting your pen from the paper. However, at the point x equals 0, the graph has a sharp corner. Because of this corner, the slope is ambiguous, and the derivative does not exist at that single point. Therefore, remember that continuity is a necessary requirement for having a derivative, but it is not a guarantee. To wrap up, let us review the key ideas about the derivative. The derivative, written as f prime of x, is a new function that gives us the instantaneous rate of change, or the slope of the tangent line, to our original function f of x at any point. We calculate it using a limit, which can be written in two main ways, as the limit as h approaches 0 of the fraction with f of the quantity x plus h minus f of x in the numerator and h in the denominator, or as the limit as z approaches x of a similar fraction. A function is not differentiable everywhere. The derivative fails to exist at points where the graph has a sharp corner, a cusp, a vertical tangent, or a discontinuity. This connects to a crucial rule. If a function is differentiable at a point, it must also be continuous there. However, do not assume the reverse is true, as a continuous function can still have a corner and fail to be differentiable. The main thing to remember is that the derivative measures the slope of a function at every point where the graph is smooth. Let us test our understanding of the relationship between a function and its derivative with these two questions. To sketch a derivative graph, we can plot the value of the original function's slope at each point along the x-axis. You do this by observing where the function is rising, meaning its slope is positive, and where it is falling, where its slope is negative. For example, at any peak or valley on the original graph, the tangent line is horizontal, so its slope is 0, which tells you the derivative's graph must cross the x-axis at that x value. For the second question, remember that continuity is not enough to guarantee differentiability. The function f of x equals the cube root of x is continuous at the origin, but its graph has a vertical tangent line there. Because a vertical line has an undefined slope, the derivative does not exist at x equals 0. The essential point is that a function is only differentiable where it has a well-defined, non-vertical tangent line.